So the first thing we're going to do is install the important packages. So we are starting with installing upgrade Google Meridian. So this is already going to install the latest version of Meridian. So obviously what you're seeing in front of you is already an executed code. This will take can take quite a while if you run it for the first time. So I'm just going to show you what's already been done. So yeah, once that's done, it's going to take like a minute or two. By the way, so I'm obviously running it on Google Colab, and the resource type that I'm using is a hosted L4. So that's what I'm using. It's based on computer units, and this is actually what Google has also recommended in their Meridian documentation, that you don't just rely on CPU. You will have to require either GPU or even TPU if possible. So either you can do that, or you can sort of go ahead and purchase a full package for Google Colab Pro as well. That's something you can do that. So the data set that we're working with, I'm going to talk about it now, is basically going to look like this. I'm showing you the first few, the first 10 rows, and you'll see that there's a date, of course, and then there is the total revenue, and these are our channels. So these are our two paid channels, Google Ads and Meta Ads. And so this is actually a work in progress. There's a lot of work that's been done in BigQuery, in the data warehouse. That stuff is being cleaned firstly as a first step while the ELT is being done from the sources. And then there's further cleaning which obviously is happening here, which I'll show here. But there are other channels that will be added here. So this is this kind of a work in progress, but you already see what's going on. This is your data set. So it was fetched up to the 10th of March, as you can see, but rule ads, web ads, and then you have impressions from these channels. And you also have clicks. So these are from Google Search Console. So these are organic numbers. As you can see, there's no other organic apart from YouTube fees. So there's going to be more data that's going to be here as well. So I've been doing this iteratively, run several versions of it already, and seeing what is the sort of impact of running with a certain number of channels and sort of trying to deduce from there. So after installing Meridian directly, you will have to install the other necessary packages like NumPy and Pandas, TensorFlow, and yeah, and then from within Meridian, you will have to import these as well: constants, load, distributors, small spec, optimize, analyzer, visualizer. This is just just copy pasting this part here. Obviously, this is what you have to do anyway. And but then you have to, the way I have done it, obviously, is uploaded the file here, and this is the text file, and this is the head section. So this part was just simply getting the data loaded into the system, and then you're looking at the information around the data, right? So what are the kind of rows that are here, and this is going to be a very important step, right? So you already see some things here. So it's an object format, right? The data type for the report date that has to be changed. That has to be handled if you have to do any kind of time-related manipulations. These are proper in float format. This is something in int that should ideally be changed, and then these are in float, and this is again in int format. So it's best to have all of them consistently in float format. So the first steps, like I said, so reported that was that was required to be changed to date time format. So that has been changed to that format here in this in day month year type of format, and then we are printing out the number of cases where there's any null values for those such clicks and impressions. So there's actually a lot of sort of small level history here that these two columns had a lot of issues. So there was a lot of effort that was being put into these columns. So sort of as a continuation of that, this has been done. Not that it means a lot here, but as you can see for the spend columns also, it has been attempted to find out the number of missing values, just to ensure that it's not too many, or it's something that can be dealt with some simple solutions. So this is the report dates for those local ad spend rows where the value is null. And again, this is NAT, that for the datetime column, for the report date column, it can sometimes contain NAD values if it's like null, and in this case, it was 0. So we did a plot of the Google Ads spend column, and just trying to understand this of course can be done for all the columns. There was a specific reason why this was being done. Specific business reason we wanted to understand where the spend was actually high, and just to sort of get a visual understanding. You can see that there's a huge increase in spend at some part of the year. That was the reason why this was being done. And yeah, so this was again another, we wanted to understand the total revenue. So this actually was cross-checking also, just to understand if you're on the right track. So, at every step, you should always know that your data is doing the right thing and you're using the right data rather as well, feeding the right thing into the system. So we were just cross-checking it with BigQuery. I just queried up BigQuery to see what's the total revenue between these dates, and sort of matched exactly, just to ensure that. And now it's the nicer time to, okay, so this has been again another plot of total revenue. The last time we saw for Google Ads. And you can see it's a really simple plot. Just define the start and end dates, and created a variable called filtered data, and sorted it by the filtered data, sorted the entire data frame, and then we just plotted it with the right kind of markers, and uh, yeah, that's pretty much it. So yeah, I was playing around with the ticks a little bit, what kind of white ticks I really required, because it was automatically setting it to a million. Okay, so it was all in the ratios of millions, so it was all like 0.2, 0.3. It wasn't very useful. I just wanted to wanted the Y column to have up to 5 zeros here. That's what it really does. All right, that's the upper Y limit. So that's why I did this custom thing, and that's how I did it. So small tricks which help visualization and analysis therefore. So you see for meta ads as well. So this is revenue rather, and interestingly, let's see, probably around the same time, or maybe not, but yeah. But there's also another increasing spike, as you can see here, in revenue now this time. So so this was to also understand the pattern here, if it's going upwards, if there's a general trend. So there was a general trend upward and a slight is towards the end of last year. So that's how the revenue really looks like. And this is, by the way, the period of the plot, because the data actually goes beyond that as well. But this was just to see a subsection of the plot, just to see the trend. And then there was data that described, which described the mean, the standard deviation, the quartile ranges, and all the other values, important metrics for dispersion and for center tendencies. And then we actually did a little bit of imputation here. We filled up some of, just a few basic values were really there for Google search clicks and Google search impressions. In fact, yeah, just one, in fact, as you can see, 486. Um, yeah. So we just replaced those with the median, and we did a describe again just to see if it really had any major changes. So obviously it didn't have any. The mean and the standard deviation we can always check. So 401 and 242, you can see they still kind of remain the same. It's just in the decimal places probably that there's a little bit of difference here. There you go, after the imputation process. But yeah, this was actually a bigger problem when um, when data set was originally available. So we had to do quite a bit of work just to get the data from the sources. The data was there, it was just not there in BigQuery yet. So a lot of history there. But yeah, so data and info, yeah. So 487, 482. So there you see some missing value rows as well. The rest are sort of all, they're all 487. data.head just to see again. So this is what it looks like, a real analysis. I mean, maybe a very advanced analysis don't go through so many steps probably, but I always ensure after every few or maybe every 4 or 5 major changes to the data set when I'm manipulating the data frame. I always check with describe info and maybe an head just to see if it's going in the right direction, just to see if it's nothing's out of place really. You can never be too careful with this. So yeah, now non-values, total number of non-values for revenue, like I said, that's why I do the info, right? That's why we do it. So just figure it out again how many value column rules were there for the revenue column. We dropped a specific data frame email that there was a 0 in it, and then we saw the data head, and then we actually dropped all the rules. That was the easiest thing in this case, and because there were not too many already. So we dropped those and we just cleaned, and we just sort of had a data underscore clean, and we saw that it's all 480 finally, and then we just, assigned that value to data. And then we did this and saw the values and saw that if it's really changing or not. In most cases, we saw that it was not having any major impact on these values. And then, so you'll see that there's, from time to time, some code which is in green, which is just to denote that something that was tried, and in this case, it's been turned off. So this is what you're seeing in front of you is actually an exercise that's been done after going through some future steps, and this was actually done to reduce multicollinearity, and this is what we haven't experienced yet. You'll see that in a moment. But the reason why we are trying to do this is essentially, as you can see, what we're trying to do is to see is to look at the quartile range, and then we are taking a lower bound and an upper bound, kind of like a Z-score sort of a thing, where we are cleaning the data based on the lower bound and the upper bound, and sort of not taking anything which is lower than the lower bound, and not taking anything which is higher than the upper. And this was required initially, but we found a better way eventually. So you can see there are still outliers even with the current data, but this is still manageable. Okay, and yeah, so there you go. This was no longer important for us. As you can see, it dropped much more the previous time, right? So this was 474. We're actually dealing with 480 now, if I'm not wrong. So we didn't have to do that. But yeah, now we are to the next phase of the analysis, which is where we're doing a weekly aggregation of the data. And the weekly aggregation is very crucial. And I'll tell you why it's crucial. Because Meridian, and it's not just Meridian, in fact, for any marketing mix model, if you're taking data at a daily level, at a very granular level, it's actually going to be more noisy. Because the daily level fluctuations are also going to be captured, and it's going to try to model around that, and probably it's going to be overfitting, all kinds of problems will arise because of that. So it's probably best to go with a weekly aggregation. And that's what we have done here. So it's weekly aggregated data, very simply done. But it looks simpler now, but it had to be actually, there was a lot of thought that had to go into. And the thought here, as you can see, is because of the fact that its minimum as you can see, reported minimum has been given here, and that's the earliest date in the week. And the reason why it's that is because initially this data set had repeated values for each day. Okay. So what I mean is that these tables were actually joined together from multiple sources, right? So the way it worked is we have to we actually had, what I had to do is to sort of aggregate it using the minimum value of the date, because the date would appear multiple times, right? So the date would have, and it's not because of geos. As you can see, this is a national data that I'm using. There are still no geos, and I'll probably do that at the next stage, and maybe we'll share an update how that went. But this data actually had to be sort of split into was split into, for multiple values of each date, for some channels. So, yeah, I mean, for all the channels. So for that reason, it was the early state that's been done. For the rest is on sub, as you can see, the aggregation level. And then, yeah, that's how it does that. And then, yeah. So now you can see that it's weekly basis data, right? And so now this was another thing that had to be done. So what this actually also did is that we had what 480 rows, right? And we, at 480 rows, all of the rows were actually not, or rather, all of the, the segregation after the weekly segregation. The difference between the different rows, because these are all now the individual time points that have to be fed into the system, right? Now, the problem is that the difference between them was not always 7. You can see that it's 7 in almost all of these cases here, I think, but somewhere inside the data, it was not. And that's why we actually had to start on, every week with a certain date and then ensure that, we follow that format always. And because of this, we had to do this resampling, and this ensured that every week was, every date point was actually 7 days from each other. I hope that makes sense. And that just is a way of resampling where do you really start the week from. And once that was done, this is how the last, because the problem usually happens at the start or at the end, right? You can understand that's where the problem happens, because then there will be a week which will probably have just 5 days, and the next week we'll probably have 7 days, and that's where the problem starts. But in this case, you'll see that it's all, having the same number of days. So that difference was going to be very, very important, because without it, then it doesn't work. Okay, and that's what at least that's what I think is happening, because it has clearly showed me that multiple times. I faced this problem. I've done all the aggregations, done all the hard work just to feed into the system, and then understand that wait, there's nothing about that. And then do the info, and then we have the, then I actually found out the outliers again. So you can see after weekly aggregation, number of outliers are much lesser. And remember that there were a couple of columns which were not, which were in int format, so just converted into float here. In this case, using the ace type, uh, just tasking them, and then there's a weekly date describe again. So yeah, this is like I said, I just keep doing this from time to time, just to ensure that the changes are right. So this is what I was talking about, the unique differences. So weekly data now has 7 only, and only for the first one is 7, because there's no week after that, right? So there's no difference to calculate. So this was very important, because till the time this was being done, it was not going to be possible to feed it to Meridian. So now we drop some of the unnecessary columns here. I think modified score was probably used something else, and in this run, it's only going to be date difference that had been dropped, or maybe week group. Yeah, so week group, that was the temporary column just to help with the aggregation. So yeah, again, there will be some green rows here which were not required, and then we are going to start mounting. We can just mount it on the drive, and we're going to save it as weekly data. And yeah. So one thing I've noticed, and this is for people who might be doing it for the first time, any data experts will already know it very well, or anyone familiar with Python, is that you should not be feeding this weekly data back into data, which was your original data frame. Because if you have to do any kind of manipulation, suppose you have done something wrong at this point, and this has happened so many times with me, even in this example as well. I can actually go back to data, that original data frame, and make those changes, and then arrive at corrected version of the weekly data, for instance. But if I, assign it at some point here in the recent rows, week data equal weekly data, then you won't be able to do that. You have to start from scratch again, upload the entire data set. So I mean, there can be other ways also, but this is how I, do it. A very simple way. Just keep the naming different, and or keep the data frames separate. Great. So yeah, so here's the file path. This is how to define it, so that it takes the file from the local storage here within Google Colab, and then we actually do a couple of other steps. These could have been done later also, but yeah, we are doing a simple correlation matrix here for all the rows except with respect to total revenue. That's all it is doing here. That's the data.core function, and as you can see here, um, it's actually pretty good correlation. I'm not saying it's very good, but it's not that bad. Google Ad Spend and Meta Ad Spend, they have close to 0.6, not over 0.6 for Google Ad Spend, and I think that's a pretty decent correlation. Also from impressions, so you can later on see that they have, not surprisingly, they are going to have very nice, or not nice, but quite a lot of multicollinearity with respect to each other. And then there's YouTube views, which doesn't exactly have any high correlation. Okay, so right, so I think there was so the seasonal revenue column, I think this somehow arrived here from a previous data set that I was working on, and I think if I were to run it now, so that's what happens. Like, I probably went back and just ran it, and that's why it appeared here, but it's not supposed to appear, right? We haven't yet done the seasonality analysis. So that's your weekly data core values here, and as you can see that there you go. So it's all 70, and yeah, this is the correlation. So again, these values will differ from one time to another. When ads impressions has come up with a small negative value, total YouTube values with a small negative value. But yeah, like I said, so this was done a little. This data is different from here. That's because there was a small change in the way the data was actually run previously. So I probably just changed it at some point. And so this is the weekly data info. This didn't have to be there because this column is not even there. And then you have the VIS. So this is what I was talking about. There's quite a lot of multicollinearity here, and I can potentially do some, try to see if I can do some, reach regression or something. But it already uses Bayesian analysis, and it has its own way of carrying out regularization. So I don't think that was going to be very necessary. It's really at the level of feature selection, or any other kind of feature engineering that can be done. But as you can understand that there's only a limited number of channels here, and there's no way I'm dropping any channels here. So even with the high PIF, I just have to carry on with multicollinearity. But this is something that you're observing after an analysis has been done. So remember, I showed a box plot a little while back. So that box plot was done precisely because of this reason. Because in that case, it was astronomically high. It was about 100 for some of the variables. But it actually became lesser once I did, that sort of fine tuning where I got rid of some of the outliers, and that actually helped sort of bring the PIF down a little bit. So to those not to those not particularly familiar, so multicollinearity is basically a concept where the independent variables, or is the situation that arises when independent variables themselves are correlated, and they actually saw from the correlation table as well that we actually have to look at this on this table here. We were obviously looking at it with revenue, but if you look at maybe Google Ad Spend with Ad Spend, that's 0.48. So that's not very low. I mean, there's a decent amount of multicollinearity. As you can see, Meta Ads, Ad Spend and impressions, that's also very high. So that's basically the source of multicollinearity. So the typical suggestion is that if you have a large number of variables, and that can often give rise to high multicollinearity, you have to drop some of the variables which are very highly correlated. But in this case, that's not possible, as you can understand. So feature engineering, or maybe getting rid, or maybe just making the distributions a little bit better, which I did in this case, getting rid of outliers. Those are the usual techniques here. Then there are other techniques like PCA, again, principal complete analysis. That also is a dimensionality reduction technique, but that's only possible when you have large number of variables. So every situation is different, and that's why it's important to be aware of what you're doing. I just redid that box plot here again, and there's going to be a few rules which are not required. because this is the situation. These are the things that I was talking about. I tried it, with different kinds of regularizations, or not, or rather outlier handling. And I was trying to see how that was doing, and finally I came up with the one which I showed you earlier, and that's the one. In fact, I even tried scaling the data. Okay, so this was min-max scaler. I could have tried other types of scaling as well, but yeah, that was eventually I didn't do it that much. I just got rid of the outliers. So now comes the actual seasonal decomposition part. So this is the manual seasonal decomposition, and just to make you aware that Google's Meridian has its own seasonality handling mechanism, and that's called nodes. Okay, so by default it's set to none, and by none is basically one knot. So if it's a national data, which is the case in which is what's the case in this video, in this data set that I'm showing you, then it's just one not for the entire time series data, which means that time doesn't really impact, right? They have a very, very good documentation. So once when I get to that part or knots, I'll actually show you the pages here that are there, and talk a little bit about it. Not much. I'll probably make separate videos on some of these aspects. There's just so much going on here. And in similar models, especially those using Aggregation. So this is the seasonal decomposition using stats models, as you can see. And from there, I'm using a very simple aspect here. So seasonal decompose, and we are having weekly data. And from there, we're obviously doing it only for the output variable, which is the total revenue column. And then we're using the multiplicative model, not the additive one. And that's what's best. And we have given a 10-week period, and we're going to see how that actually looks like. So this is how it looks like. And yeah, so that's your original. This is the trend. And that kind of matches, right? We just discussed that under a while back when we looked at the revenue, right? We saw that it goes up a little bit. It kind of has a dip as well. So that's the trend that's being extracted. And this is the seasonality that's been extracted with a 10-week period. So that's what we did. Yeah. And that's the residuals then. So that this is a normal seasonal decomposition. And once you have the residuals, so that's going to be you're going to have a seasonality factor that's going to be added to your data frame as well. So this is just a comparison that was being done for the different values of the seasonal decomposition period. So 7 is here, 10 is here, 13 is here, 26 is here, and just a comparison of how it looks like for each of these cases. So the idea of this is to have a visual understanding of what actually looks the best when it when this is decomposition has been done. So if this has been done, residual ideally should look very random. That's the whole point. If it still has more seasonality, just like there are recurring things happening going on, periodically, then there's still not enough seasonal decomposition being done. So either you increase the seasonal factor, the number of periodicity, or you just change your model altogether, your approach of doing seasonal decomposition. So there's a lot related to seasonal decomposition. I recently made a video on Facebook Profit as well. I discussed some of it there. Auto-based models are there to understand it better. And then there are, ACF class, basic class. A lot of things are there for time series decomposition. But yeah, like I said, this is the custom one. On top of it, you can actually assign something, which Meridian already has, and that's the concept of splines or knots. So how you can set the number of knots and actually decide how the baseline is going to look like. So the knots basically decide the baseline. The baseline is anything that's that contributes to the revenue apart from your explicit marketing activity. So that's basically the baseline. That's what the knots does in terms of seasonality. We're going to come to that. So this is again looking at the data once the seasonal total revenue has been added as a row, as a column, and so then again doing the head thing. That's what I always do. So in this case, what had happened really is the weekday had moved to the right hand side. So I just got it back. So yeah, my runtime got disconnected, which is fine. I'm not really running anything as of now. And then there will be a few rows, we get a few cells which we're not really going to run. Now we come to an interesting part. So now we come to the part which can give you a feel of trend test, right? And this is what who are working with data, we love to do that always whenever we're running models. We like to split the data between training and test, right? Because we want to do some kind of validation. So this is, of course, from the same distribution. As always, the holdout has to be from the same distribution. And so we are just doing a trend test split here on that one, 80-20. And the method that we're using is we are basically creating a TensorFlow holdout ID, and we are converting them to tensors. And so, yeah, the way we are doing it is using random.choice. As you can see that there's no random seed here. So as you understand, if you are already into data science, you would know it very well that when we are doing this split here on the rows, as you can see, so as you can do with the data shape 0, which is working on all the rows, it's actually recommended sometimes if you want to do np.random seed 42, set a value for a random seed, then it's going to be the same split every time. Otherwise, what happens is if I run this, every single time, I'm going to get a different training and a different test split every single time. So the outputs will vary. But if you want to set it in place, then this is what you can do, or you can use similar sort of trend-based split, maybe from sklearn, and simply define the random structure. So that's basically for reproducibility of the results. Now we are going to define the local file path, and then we're going to pass the Wikidata there, Wikidata data frame. This is the part which is a specific thing related to Meridian, which is when you do something called coord columns syntaxing, and this is where you sort of inform the Meridian process that which specific columns or which specific variables correspond to which channels. So we get as the time, we define controls as seasonal total revenue. So that's a seasonal decomposition component. And then we have impressions and clicks. So remember, these should ideally be confounding variables. So that's the concept of Meridian, and indeed of any modeling that's using causal inference. So these have been passed into the controls part here. And we are using KPI, which is total revenue. The media is Google Ads impressions and Meta Ads impressions, media spend that is spent from these two. And this is how you put it in here. Okay, so this is organic media, which is totally diffuse. And then you pass in the correct media channel these Google Ads impressions, which is again, you just show the correspondence. So Google Ads impressions corresponds to Google. So the naming convention should ideally be good. So if your original file name does not consist of channel names, then ideally it's best to do that and do the correspondence in this fashion. And then you have the loader part where you just load the CSV loader, just repeat these steps here. The KPI tag is revenue now. Case it can also be non-revenue. This documentation. There's notes about that in the documentation as well. Coord columns, that was the name of our variable having the coordinations. And then we also have media spent channel, which is the correct media spent channel. So that's pretty much it. It's not particularly difficult unless you're having some sort of complex definition, a complex way of assigning values. And you can see there's a green part here. This is where you can sort of have one ROI view and signal. So this is the part where you're setting the custom price, by the way. And you're setting custom price by, you can do it in two ways. You can either pass one value for all the channels, or you can pass it by assigning multiple custom price, and this is our ROI price, as you can see, for each of the channels. So in our case, we only have Google and Meta, so we are passing 3 and 2, which we'll see that is a little bit on the higher side. By the way, the in-platform revenue was very high here, and that's precisely it's such a good use case actually for running MMMs for a high spending project. So the in-platform ROAS was so high that it almost surpassed the revenue in the store for some period. So yeah, the ROI is, but it's sort of estimated. And I've actually done multiple iterations of it. You're only seeing one, and then there's the sigma the variance as well, or rather the standard deviation as well, the 0.4. So 0.5 and 0.4. So that's kind of like a thumb rule. It has to be a fraction of the ideally from of the mean. And now is this part here. So I'll actually talk about this NOTS part a little bit later. Just let me quickly walk through a couple of lines next. So once you have assigned ROI price, now you have to, this is basically predefined already within Meridian documentation, where you pass it on to a variable called prior, the prior distribution. This is where the sampling is going to be done. This is what is the basis, the core or the fundamental aspect of Bayesian analysis. And then there's model spec. There's a model spec object here, and you're assigning some arguments here. So prior is prior, and this is where you put in the holdout. So remember, we did the holdout a little while back. This is where we had the holdout IDs. So those holdout rows, they will be passed on here in the model spec object. And then you finally call the Meridian model object as well, and once again passing the model spec and the input data, right? So that's how we are defining this entire thing. And now this one part that I left out, I'll quickly explain as well. The next part actually is now the sampling from the prior, the sampling from the posterior, come up with the final posterior distribution. And you can play around with this hyperparameters. You can play around with number of chains, the number of n-adapt, number of burn-in, number of LT, just to see what kind of an impact it is. It's ultimately using Markov chain multi-column, remember, MCMC process of sampling, and it takes a while, by the way. So I don't know if yeah, there you go. So the last time we ran it, it took 7 minutes 41 seconds. It depends on your size of your data set, which of the resources you're using. So you can see in this case, the runtime I'm using is L4, like I said. So, it depends on all of these factors, how long it's going to take, and also how many of these samples you're taking here. So there you go. Or how many iterations you want to do. And so yeah, now I'm going to come to the NOTS part. So the NOTS is, like it said, it's the built-in seasonality thing of Meridian. And Meridian has a very nice documentation of how NOTS argument works. And as you can see, that there's some linear algebra going on here. And I'll probably talk about that separately later. Otherwise, it will become too long. And so you will have, so n times is essentially the length of the data set, or rather the number of rows. So it has to be between 1 and n times. So 1 is the minimum value, and 1 is when all the time periods are measured with a single parameter. Like I said, that's equivalent to saying time is row effect. Yeah, I would definitely suggest you go through the documentation if you're serious about implementing this yourself, then look into it deeply. But yeah, there's a bias variance trade-off. If there's too many knots, then there's going to be overfitting and high variance, and maybe if there's too few knots, then there's going to be maybe underfitting and um, yeah. So there you go. So you can use knots less than a number of times, and you can decide how much it's going to be correct, because this depends on the number of seasonal variations, the number of seasonal sort of number of seasonal variations that are there in your data set, right? So if your data really is varying massively in some places, and you're aware of it, or you can see it from visualizations, you can just play around with knots. And the good thing about setting knots is actually you can set it for specific periods as well. So Meridian also has has the documentation article. Go to the user guide to do that. You can go to the settings, I think, from here. Yeah, so you can configure the model. I think that's where you can probably get the knots spot. Yeah. So yeah, this is the holdout part, and this is where you can get the details for how to set the knots, right? So you can they recommend to start with say 0.8, right? So that's like 80%. So 80% of the data has been split up to get the uh, yeah. So so that's the number of knots that you will have, 0.8 into the total number of rows that you have. But you can reduce it or increase it depending on how many knots you think is going to be actually correct for your data set. So that's the way it was done. And in this case, when I actually ran it, it came out with a baseline, and I'll just so yeah, so it actually came out with a baseline. I don't think I have that one here, but which actually gave a negative baseline, but more importantly, it gave very poor R squared values as well. And it wasn't so what it was really doing is it was overfitting, right? It was trying to put in too much too many sort of variations, and there were not that many variations, right? So that's where you have to do a little bit of experimentation. You have to decide what's going to be the value here. You can reduce it. You can define also the number of knots instead of directly instead of just using this sort of a method. You can say these are the points, these are the indexes at which the knots will be passed. Okay. You can also say at every four, so you can have knots at every at an interval, say every 4 time points. So there are multiple ways you can define the number of knots. You can have a specific value here instead of in this way as well. And you can test for these different values, and that's one way of really deciding on the seasonality. So once the sampling has been done, that's when you do the predictive accuracy table, and you can see that the holdout table that's how it's been done. The holdout IDs did the trend test split, and that's why we have the data in this format. So 0.73, 0.37, and 0.65, and so that's what we really have here. And so yeah, the map, as you can see, is also given in the form of trend test split as well as the W map here. And you'll see that for the test one, it actually didn't perform as well. It was almost half the R squared. So yeah, it really see there's more work that is to be put in. So in this case, actually, and like I said, this is a work in progress, and you see something it's kind of in flux. There are more channels that can be added as well. And so that's the scenario then. And this is the R hat plot and the R hat plot for the different parameters. As you know that the R hat will be convergence, will be indicative of convergence if it's greater than 1. And in fact, if the closer it is to 1, it can't be less than 1 really, ideally. But if it's very close to 1, then it's very good, right? The closer it is to 1. In this case, as you can see, the variation, the IQR is a little bit high for these two gamma parameters. Then you also have the model fit. So now you do the visualization of the fit, and as you can see here in this case, so remember what I had said about knots, and also about the holdout IDs. That if you don't do the random seed, so this was, as you can see in this case, I didn't do the random seed, right? And that's why this, every time I actually run this, there's going to be a different output. And so in this case, this is the other output I'll show you. So it was actually using almost the identical, the data set was identical. Everything else was the same. The only part different was the holdout IDs. And as you can see here, the baseline is entirely above 0, but more importantly, the R squared was say 0.67. In this case, you'll see that the R squared is 0.65, right? And let's see the MAP here. The whole data MAP is around 12%. W MAP is around 11%. So the errors are a little bit better. The R squared is a little bit lower. But yeah, but the baseline here just goes a little bit under zero in some places, which is not great. But Meridian in its documentation has already mentioned also that the baseline can sometimes go below 0 as well. It's not necessarily a huge problem. You can see why it's happening, because 87% of the contribution is actually being estimated by this model to be coming from the channels that have been, for which the data has been passed to it. So yeah, I mean that kind of shows that there's an overfitting to these channels, and part of it, of course, comes from the fact that there's that there's multicollinearity as well, right? So there's a sort of overestimation of the effectiveness probably, but you can read Meridian's documentation. It really discusses these things very well. Somewhere down the line, but it sort of really tells you nicely that some overfitting is actually good, in the sense that you're trying to fully understand the impact of these channels, because this is not meant to be 100% accurate. This is meant to be directional. That's the whole point of MMM. It's the only way you can really try to fully validate it is to run some experiments side by side. But the idea is that you should not try to be so accurate that you're underfitting so much that you don't really get a full idea of the impact of the channels. So this is the waterfall chart now, showing the impact of the channels. As you can see that the baseline is pretty small. It's around 6.7%. In this case, I think it would be higher. So you can see that it was 15.3%. So that depends on your holdout set. Since I didn't, I kept it completely randomized, and I didn't keep the split the same, even if the actual selection of or the assignment of the training and test rows was random. But every time the random was also being randomized. So that's why in this instance it came out with 6.7% as the baseline. And then so we already did the outer sample predictive metrics, remember? So we already have this data, right? And you'll see that we have the accuracy metrics also from this method. So we used in the previous case, in order to get the outer sample predictive metrics, we simply used the visualizer, right? Model.diagnostics, and but in this case we are using the analyzer. Okay, so from the analyzer we are drawing predictive.accuracy, and then we are assigning it to accuracy metrics, and this is what it gives us. So this is called an X array, and this is also a case where what I earlier done while I was doing this exercise is I shared with ChatGPT, and that I've shared the sort of uploaded this data, this X array, and I also uploaded the table. So these two actually have the same values, and depending on if I had done the run at the same time, I don't know if it's same right now. So yeah, I think it is. So these two actually have the same values. The X-ray is just giving the table data in a different format. But I asked ChatGPT, I just tried to see what its feedback is going to be. And it completely misread the X-ray, and it told me that, hey, the values are different for both the cases. So I'll be sharing that as well separately in a LinkedIn post. You can check that out. But yeah, so this is what I wanted to point out as well, that don't always rely blindly on ChatGPT or LLM tools. You need to know your stuff. Otherwise, you can really get bad names there. So then you can just have the summarizer, and then it's going to give you your output for the defined date range. So, for this particular run, I haven't actually done that, but this is what it looks like for the previous run. So as you can see, it will have the model fit. Let me zoom out a little bit for you. So it will have a model fit, which shows you the expected versus actuals. And it's a pretty decent job, right? It of course doesn't get it right for a few of the places, as you can see, like in this particular case here. And this is where you can do so much with playing around, right, with your hyperparameters. With some sort of tuning, you can tune your seasonality coefficient. You can see how better you can do the decomposition to try and see if this is really a seasonal thing. Or maybe with the Knox factor, you can do that. There's also something called a max lag parameter. So you can do all kinds of things, to try and improve it. You can dive into the reference, by the way. So the API reference has, all the methods and the attributes, right? And you can check out how you can play around with this to sort of come closer to the actuals. But yeah, understand again, this is having, or in fact, this is without a holdout, like the one that you're seeing. But even if it's with a holdout, the holdout is always coming from the same distribution. It's very important to remember that. And so, you don't really want it to be overfit, right? You just want to get a decent trend that matches the data. Because if you have a data which is slightly different, quite a bit different, then if it's overfitted, it's not going to perform well there, right? And it's going to be high variance. So it's better to, or it's not going to capture the variance well. So yeah, just keep that in mind. 6.67 was the R squared here. This was the distribution. It assigned the highest to the, sort of contribution to Google, lesser to Meta. And so yeah, I mean, there's another thing you can do here, which is to actually see the percentage of spends by channel and compare it with the percentage of contribution that's been forecasted as well, right, by the model. Not really forecasted, but rather explained or estimated. So 15.3% was the baseline here. Spend and revenue. So you can see that Google has a sort of high spend as well. Yeah. But not that much, right? I mean, in terms of the contribution, Google's contribution has been estimated to be much higher. So Meta is not being very incremental. That is the outcome. That's the outcome analysis, a very important analysis, and this can help you set budgets. You can take future decisions as to what will be the optimal budget distribution based on this analysis. Again, in the form of a pie chart, and this is where you have the return on investment versus effectiveness. So it just shows you that just because some channel has a higher ROAS, for instance, in this case that's not the case. The ROAS is also higher for Google, but it also has a higher effectiveness. But in some cases, it might be the opposite. The ROAS may be higher, but the effectiveness may be lower. So just to see the balance and the trade-off between these two. Same thing with marginal ROI, and they just happen to be very same in this case. And then we have the 90% credible interval for the ROIs by channel, and it's a pretty decent, upper and lower bounds here. That's not too high, and much higher for Google. Remember, by the way, this has not been done yet with campaign type splitting, so you can actually exclude branded data, which I've done in previous iterations for some other cases as well. So you can always do that. You can exclude, campaign, some campaigns which you think may not be incremental, and then actually do the analysis. So in this case, they report a lot of branded data, branded search campaign that I'm talking about, which is also included here. So that might change, so that's going to be another iteration that's going to give us a completely different story. So this is the CPIK and the cost per incremental revenue, the cost per incremental KPI. And then you also have the response curve. So the response curve here you can see for Google is on the much higher side, and this also saturates, less faster than Facebook, as you can see Facebook as a curve which is far more parallel to the x-axis because it's strong. It's just being saturated much earlier. That's what it predicts anyway. So this is the current level of spend, by the way. So this is the output. I think it's a pretty cool output. The one thing that I've not shown here is really the budget optimization part, and I think that has so many nuances to it. Optimization itself is a huge topic. Meridian has its own built-in budget optimization technique, but you can do it in a more advanced way as well. Take the data out from here and do it yourself separately. That's also possible. I mean, but yeah, I'll probably show it separately. I'll probably also talk about the knots part separately and some other aspects of maybe Bayesian aspects. I've already shared previously a video on Bayesian updating. Do give it a watch if you're interested. So this was the whole thing. I know there's a lot to take in, especially if you're not very technical, not very updated yet. But I think this is a great great tool at your disposal if you're looking for something so complicated and so advanced as marketing mix model. But yeah, I mean, relatively speaking, this is still simple, I would say, because I think there are some other open source solutions which probably a little bit more complex, at least from what I've seen. But yeah, this is one of the relatively easier ones, but then there's a lot of customization that we still have to do, as you can see, a lot more which still needs to be done in the case that I showed. So hope this was useful. If you have any questions, do leave them in the comment section below. We'll be more than happy to take up a conversation. And yeah, see you in the next video. Thanks for watching.